All right, so in this problem, we want to compute the vertical displacement at and rotation at C, which is out here at the end. We'll just go for the deflection first. We want to include the effects of bending and axial force. So as I create my sections, I'm looking at internal forces. I'll go ahead and get the force and the moment at each section. So let's do a little strategy first. So when I'm looking at the real moments, if I cut the structure somewhere here between A and B, which one do you think is going to be easier to work with, the top half or the bottom half? It kind of becomes a little bit of a toss-up here. If you do choose to work the bottom half, which is okay, you're going to have to find these reactions. You may or may not want to do that. If you do work the top half, you can do that. In fact, I may do that and define my coordinate as going from the top down to make it easier on the calculation. So I'm going to think about that one for a second. When I do cut it here from B to C, though, I think it's much clearer to see that one. If you're looking at this L-shaped left side, which would include the reactions and all this force, or just the right-hand side, I think the right-hand side is going to be the clear winner there. So now I've thought about it a second, I think I'm going to go this way. So I don't want to have to worry about getting my reactions right now. So that would be my virtual system. Could I use that same setup, my real system, could I use this same setup for my virtual system? What would be my virtual system? All these loads would be removed, and I would just have a single unit load here at C. So that section would still work fine, and the right-hand side would still work fine. So I think it's going to work out. So let's get started. I'll do the real loads first. So starting with that, and I'm going to do this section AB. You can see I decided to use the top part of it, so I'll draw that in here. So there's my structure. Out here at the end, I have my 10 kip force. This is a distance of 10 feet. And I'm going to, let me do it this way. I'm going to draw it in this direction called Y. And then I have the distributed force, which I can make a concentrated equivalent value of. Right here. So you notice that the force is basically 1/2 a kip per foot. So this force will be what? The base is y, the height is 1/2, so this is going to be y over 2. See that? And the distance from the cut in this direction, interestingly enough, is also y over 2. And then internally, I have the moment in AB and the axial force in AB. Any questions about that? Did I account for everything? I think so. So let's sum moments. So I'll come up here, I'll use right-hand rule for my sign convention, and we will sum the moments about the cut surface, make sure everything's in equilibrium. So about the cut surface, this moment at AB is negative with my sign convention. About the cut, this force y over 2 is positive or negative? Negative. So the force is y over 2. It has a moment arm of y over 2. And then this 10 kip force also creates negative moment. And what's its moment arm? 10. So the moment in AB is going to be negative y squared over 4 minus 100. And that will have the units of kip feet. Okay? So how do I find this force? Some forces in the y direction. So I'll assume up is positive. So when I'm summing my forces in the y direction, make sure it's in equilibrium. I've got this force acting down. And the only other vertical force is that 10 kip force also acting down. So it looks like the force in AB is minus 10 kips. So AB is in compression. Any questions about that? That didn't look too bad. So now we want to go to the next section from B to C. So I want just this little section here. I've got the 10 kip force out here on the end. I'm going to measure it in this direction and call it X. And then internally here, I'm going to assume my moment from BC is positive in this direction. And then my force is positive in this direction. That looks pretty good. I didn't leave anything out, I think. So now, let's make sure it's in equilibrium. So I'll sum my moments about that cut that I made. Make sure it's in equilibrium. And then what do I have? Well, this moment with my sign convention is negative. The 10 kip force about the cut creates negative moment. It has a moment arm of X. So it looks like my moment in BC is negative 10x. And that would also have the units of kip feet. How do I find this force BC, this axial force? Yeah, some forces in the X. So I'll assume to the right is positive for my sign convention. So I'll sum forces in the X, make sure it's in equilibrium. And then really all I have is the force BC. So it's 0. There is no axial force in BC. Okay? So now I need to do my virtual system. So what does my virtual system look like? Well, I've got the same... Oh, got a little off there. That's okay. I've got the same basic frame, except my virtual force, since I want the vertical displacement at C, I go to point C and I put a vertical unit load. So by assuming it's acting down, that assumes that point C is going to move down. If I get a positive result, that's correct. If I get a negative result, it's actually up. And I'm going to do the same cuts as before. So I'll cut here, work the right-hand side. I'll cut here and work the top piece. Now also, when I make those cuts, I'll use the same coordinate that I used before. So now, in the virtual system, let me draw a little line here to kind of separate those. So I'll start here. This is A, B, C. So just like up here, I'll do A, B. I'll pretty much draw the same free body, except all I have on that is my unit force. This is 10 feet. Down to the cut is Y. At the cut, I have my virtual moment and my virtual force. I'll just use a lowercase f for that. So let's find those values. So again, I'll sum moments about the cut at that distance y from the top. Make sure it's in equilibrium. So looking at my moments on this system, I have my virtual moment. That's negative in my sign convention. And then what else is on there? Just the unit load. And it also creates negative moment about the cut. So that'll be minus 1 times a distance of 10. So my virtual moment is equal to negative 10 feet, odd unit. Now I need to find the axial component, which is in the y direction, so I'll sum forces in the y direction. Make sure it's in equilibrium. So I have this virtual force acting down, force in AB, and my virtual force is also acting down. So I've got a virtual force AB equal to 1, no unit. Say again? It should be negative 1. Thank you. So the last little piece we need to do would be the BC section. We used this type of free body before. We'll have the same one this time. Except the force won't be 10 kips, it will be 1 kip. Also measuring from right to left would be X, and then on the cut surface itself I would have the virtual moment in BC and the virtual force in BC. Now looking at these two free bodies, what's the only difference? This is 10 kips and this is 1. So all my results here I could simply just divide by 10. So what would I expect my virtual moment to be? Negative X. Let's see if we get that. So I will sum moments about the cut. Make sure it's in equilibrium. So my virtual moment is negative in sign. Oh, BC. Sorry, I messed that up. That's BC. And then the moment due to the 1 is negative 1 times X. So the moment in BC is negative X. And that again has a weird unit of feet. And then I'll sum forces in the X direction. This one should not be very surprising. I have just the force acting to the left, force BC, nothing else is happening, so it's 0. So now what do we do? I just need to put all that together, right? So now the displacement at C is going to be the integral from A to B of the virtual moment, or the real moment times the virtual moment, divided by EI, plus the component from B to C Now that takes care of the bending. What else do I have? The axial component, right? So then I would add to that the force in AB times the virtual force in AB times the length of AB divided by AE plus the real force in BC, the virtual axial force in BC, the length of BC divided by AE. So that's all the pieces I need to do.
So do we need to put the beams in there? I mean, is there going to be 0?
What's going to be 0?
The last thing you just wrote.
The axial part?
Not the vertical, but the horizontal, the BC.
Well, this is the complete statement for everything in this problem. Well, we haven't filled in the blank yet, but we already know that in BC, what's the virtual force and the real force? 0, right? If you go back and look, the real force in BC and the virtual force is 0. So this one is not there. I do have an axial force in AB, and I have bending in both of them. So let's see if I can fill in the blank here and see what we get. So I'm going to integrate from A to B. Remember my unit was Y, and I went from the top down. That's going to go from here to here. That's from 0 to 20. The real moment is this, right? So that would be y squared over 4 minus 100. So that's my real moment. What's the virtual moment? Minus 10. And of course that would be divided by EI, and I would integrate that in the y direction. The second one, BC, starts at the right side and goes this way. That's going to go from 0 to 10. So this is an integral from 0 to 10 of the real moment, which is negative 10x and then the virtual moment is negative x. And divide that by EI, integrate that in the x direction. And then we need to add to it this piece, which is the real force, virtual force, length divided by AE. The real force was minus 10, the virtual force was minus 1. 10 kips, minus 1. The length of AB is 20 feet. And divide that by AE. So that's a more complete statement. Just wanted you to see all the pieces put in.
Can I ask you a question?
Yeah.
When you wrote the integral from 0 to 20, you did in respect to y, but up top it's in respect to x.
Where do you, well, these are dummy variables, right?
Okay, that's just.
So when I actually got down to the equations for AB, remember that I decided to call my variable y. I wrote everything in terms of y. So that wouldn't be hard to do. I don't want to take up any more class time to do this, but you can see that's not going to be very challenging to do. This would be good enough for me if you wanted to stop here, if I asked you to do this on the exam. Now what I'll do is I'll go ahead and finish this in the office, and when you see this posted online as the PDF, you'll see the final solution. But I think this is good enough for us today. Okay, any other questions?